recording. Yep, so it is. Notability. Okay. So this is obviously the revision for my section of the module. So important things for you to know are that, so first there'll be 3 questions in the exam from my section. I think 3 questions from Dr. Lewis's section. You have to answer 2 from each section. My questions, so this is my questions. My questions will be slightly different to previous years, okay? So you can use previous years exam papers to revise, but understand that it will be different in the sense that, it goes into a bit more depth, the questions this year, okay? But if you are confident in understanding and answering all of the questions, practice questions I went through in the lectures and tutorial, then you should be fine, okay? So definitely practice on all of those. So those are the levels of complexity that you can, the maximum levels of complexity that you can expect. Okay, so it's important for you to practice those questions, for you to do it yourselves and be able to understand and answer them. Okay, so I'll start with the heat transfer part involved with radiation, conduction, and convection. So what's involved is understanding the 3 modes of heat transfer and calculations around those modes of heat transfer. But the main focus, to be honest, is on conduction and convection. Sometimes there's, as you saw in the lecture series, there's a little bit on radiation, but most of it was focused on conduction and convection. So with one-dimensional steady-state conduction, you have, let me go back a bit. You have essentially 3 types of problems. You have the plane wall, the tube wall, and the spherical shell. And then for all of these systems, you can, there are sometimes more complexity by making them composite systems. So multiple plane walls stacked next to each other, a tube wall with, for example, layers of insulation on it, or a spherical shell that has, again, layers of insulation on it. So in those instances, they become composite systems. So the same principles apply, the basic principles, but you have to add several layers of into the formula. Okay, maybe for this part, let me go back to the notes I made for myself. Okay, so obviously you have for conduction these are the formulas. So for heat flux, this is a formula, and for heat rate, there's the area component. And so I've listed the 3 different types. So conduction, convection, and radiation. It's very easy. You should know these by now. And then sometimes there is the radiation and convection combined. So for that, you just simply add the 2. Yeah. The important thing to note here is that when you're doing for radiation, because the temperatures are to the power of 4, you have to convert them to Kelvin first before you do that. For the others, because it's a difference, it doesn't matter if it's in Kelvin or in degrees. Okay, so a useful way to attack these heat transfer problems is to look at them in terms of thermal resistance. Okay, and Yeah, so thermal resistance. So you have R total is equal to the sum of the individual resistance, and that is equal to the difference in temperature divided by the heat rate, which is then equal to 1 over the overall heat transfer coefficient times the area. Okay, so this is a very important formula for you, right? I mean, it will be given in the formula sheet when necessary, but you should be able to know how to use this formula. This is very important. So to work out, if the question asks for you to work out the heat rate, Q, then this is where you go. Q is equal to the temperature difference divided by the sum of all the thermal resistance. Okay, so then you also need to know how to draw thermal circuit diagrams. Okay, so here I've given an example for a composite plane wall, right? So it's got 3 layers, it's got a hot fluid on one side, a cold fluid on the other side, and it's got 3 stacks. Okay, so these circles are there for the indicates the surface or interface of fluid temperature. So we have a fluid temperature here, which is this, and then we have resistance. So the heat transferring from here to here, there's going to be thermal resistance. So that's indicated by this squiggly line. And then you have the next surface, again, resistance through that. And then you have the other surface, the other surface, other surfaces, and they all have resistance in between. Then you have the formula for the R above it. Okay, so you need to be comfortable in drawing these. What's the other thing we need to know? Okay, so remember I said we have 3 types of problems: the plane wall, tube wall, and spherical wall. So if it's a plane wall, it's fairly simple to determine heat flux. You have the Fourier's formula. Heat rate is in this form where area is involved, and thermal resistance, yeah, R, is L over Ka. Okay, simple. So depending on the number of walls you have in a composite systems, you would have to add that. So if you have 3 walls, it will be L over Ka plus L over, let's say, K2A plus L over K3A, for example, if you have 3 walls in a composite system. So I hope that is clear. So now, if you then have a tube wall problem, the formula becomes K times the difference in temperature divided by the radius times ln R2 over R1. Here, where R2 is from the center to the outer wall, and R1 is the inner radius. Okay. And note here, for the plane wall, the direction of heat transfer was x in the x direction. Here, the direction of heat transfer is along the radius. Heat rate, again, same thing, but an area component added to it in the form of 2 pi 2 pi L, sorry. Yeah, 2 pi L. So that's the area component added to it. And again, the thermal resistance, this is important for you to know, is then ln R2 over R1 divided by 2 pi L K. So there's the area component in there as well. Then the third type of problem you may face is the spherical shell. Again, here, the heat transfer is along the radius of the shell, and it's for the flux, it's K times the difference in temperature divided by the radius squared times 1 over R1 minus 1 over R2. Here, R1 is the inner radius, R2 is the outer radius. And in the heat rate form, you have the area component added to it as well. And the thermal resistance again is important here. Okay, so that is that. So I'll go back to my notes. So important for you to know how to draw these diagrams, important for you to know how to use R to work out Q. Okay, so also in composite wall systems, you may have contact resistance, right? So contact resistance is important. And these, so for example, if there's a binding material joining two layers together, that material that binds it may have thermal resistance. So those values will be usually given to you. So it will say, like, for example, you have a composite wall, and between the composite wall, there is, for example, a solder or a welding taking place, and then the thermal resistance for that is R equals whatever. And so it's important for you to be able to use that in your calculations, not to ignore it. Again, this is going into composite wall systems, again, going into the tube wall in detail, composite tube wall, spherical shell. So just as an example calculation for, let's say, a conduction problem, this is one of the questions that we went through in last week and the week before in the lecture. So you have a spherical container with negligible thickness holding a hot fluid and having an out. So this spherical container has an outer diameter of 0.4 and is insulated with 3 layers of each 50 millimeter thick insulation. And these layers have the following K values. So in the exam questions, I always include a schematic so you don't have to draw it yourself. But in this question, I don't know, I drew it myself when answering the thing. So usually you're provided with the paragraph and then a schematic, just to make it a bit easier. So here from reading this, we identify, because it's a spherical container, that it's a spherical wall problem. So then we know which formulas to use, right? QR, we want that form of the formula. And then from that, remember, it's easy to work in thermal resistances, right? And we know QR is equal to the change in temperature over the sum of the thermal resistance. So the question is asking for determine the heat loss, which is Q. Yeah, so we know we got to use this and this formula, and we need to work out a formula for R. And so we know this is the formula for R, which, yeah, this is the formula. Okay, so then what I like to do is work out the resistances individually. So I've gone and worked out R1, R2, R3, because you have resistance 1, 2, and 3. And we know the temperature inside is 140 degrees, the outer temperature is 130 degrees, and we have the K values for each of the layers, and we have the thicknesses of each of the layers. So first thing I did was work out, write down what R1 is, work out what R2 is, R3, R4, yeah, and then go and work out my R's. So basically plugging the values in to the formula that we know, the correct formula, which is this one. So we have then get our R values. Then we plug it back. We know the temperature difference is 140 minus 30. So here and here. So that's the temperature difference. And we know, now we know all the R values. So then we got a Q value of 21.59. Second part of the question is to determine the interface temperatures of the insulating layer. So we want to know T2 and T3, because we know T4, the outer temperature, and we know the inside temperature, T1, is 140. So again, this formula is useful, right? Because the difference in temperature at the top can then be expanded to, let's say, for example, T1 minus T2. And we already know what we've already calculated what R1 is. So we rearrange to make T2 the subject and then it becomes this form. So Q times R1. So we know Q, we've calculated Q, we know what R1 is from our previous calculation, and we take it away from T1 temperature, which is given. So the interface temperature T2 is 54.19. Now that we know T2, we can go on to work T3, so which would be QI equals T2 minus T3 divided by R2. Yeah, so T3 then becomes 36.6, 36.8. Okay, so this is an example of a conduction problem and using the resistance approach to calculating Q and calculating interface temperatures and so on and so forth. Does anyone have any questions? Any questions? Okay. Okay. So then we go into convection. Okay, so it's important for you to be familiar with what a velocity boundary layer is, understand it, so and be able to draw these schematics and label them. So here you have the fluid velocity here. So in contact with a flat plate and the movement is in the x direction. So the fluid is moving. As it contacts the plate, a velocity boundary layer develops. Yeah, this is the velocity boundary layer. Okay, I'll go back to my notes again. Yeah, so velocity. So you should be able to draw these. So velocity boundary layer develops. So this length of the arrows here indicate the extent of velocity. So obviously the plate is stationary. So the particles closest to the plate are at a lower velocity. And as the distance from the plate, so as y increases, the velocity approaches that of the free stream velocity, which is given by this. So outside of the boundary layer, you have the free stream velocity. Below the boundary layer line, you have diminishing velocity as you go towards the plate. Okay, what causes this change is this shear stress causes by the velocity, the fluid is moving, the plate is in, and the friction, the shear stress causes this this gradient in velocity. So basically, you should be able to draw this, and label. So that's the velocity boundary layer. You can also have a thermal boundary layer. So that occurs when there's a temperature difference between the plate and the fluid. Now, that temperature difference can go in either way. Either the plate can be hotter than the fluid, or the fluid can be hotter than the plate. How do we know what situation we have? An easy way is to look at the line, right? So the longer the line, just like the longer the line here, the higher the velocity. The longer the line here, the higher the temperature at that point. So as you can see, the line closer to the plate is longer than lines further away from the plate. So this tells me immediately that the plate is at a higher temperature than the fluid. So again, as you go further from the hot plate, the fluid, there's a decrease in temperature difference. Above, so this is the line for the thermal boundary layer. Outside of the thermal boundary layer, there is no gradient in temperature. So the fluid above the free stream fluid temperature is homogeneous. There's no gradient. But within the boundary layer, there's a gradient. So higher temperatures closer to the plate, lower temperatures further away from the plate. Okay, so going back, then we look, so we are now dealing with convection problems, right? So fluid can flow over objects of arbitrary shape. So in these instances, it's important for us, remember H is the convection heat transfer coefficient, right? So in these cases, it's useful for us to differentiate between local heat transfer and average heat transfer. So this object has uniform temperature, right? And the temperature of the surface is different to the temperature of the fluid. Therefore, convection heat transfer will occur. So whenever there's a temperature difference between a fluid and the surface, convection heat transfer will occur. We know that heat flux and H, the heat transfer coefficient, can vary along the surface because it's an arbitrary shape or whatever it's therefore the heat transfer rate Q can be obtained by integrating the local heat flux. So here we did it as a question as well. We are basically relating the local heat transfer to the average. Average is given by a over bar, right? So this is important for you to kind of understand and know how to go from show the connection between the local and the average. But we went through it. So for special cases of flow over a flat plate, so this is in the case of any shape. And then if we want to be specific to a flat plate, then H varies only along the X direction. Yeah. So then H, the average heat transfer coefficient, H bar, is related to the local via this formula. Okay. What's the other thing we need to know? Yeah, so I'm sure you're all familiar with laminar and turbulent velocity. So this is in situations, many situations, where you have, we basically, for us to determine convection heat transfer over, we need to know the type of flow that's taking place, okay? And we can have obviously laminar flow, which then transitions into turbulent flow. So the formulas that we use to work out heat transfer will depend on whether we have laminar flow or we have turbulent flow, or if we have a mixture, which is in the transition state. Okay, so you should know what formulas to use depending on the type of flow. So to determine the type of flow, you would have to work out the Reynolds number. Okay, and that the Reynolds number falls under a group of non-dimensional numbers, and another important one is the Nusselt number, which represents the ratio of convection to pure conduction heat transfer. Yeah. And again, Reynolds number, I won't go into it, but you have, you know about it. And then you got the Randall number. So those are the three numbers that can come up essentially. Maybe I'll go to my here. So again, as I said, so you can have laminar or turbulent flow, and you can have a mixture. So essentially, you use the appropriate Reynolds formula to work out whether it's so if it's flow in a tube, use the appropriate Reynolds formula. If it's flow over a flat plate, use the appropriate Reynolds formula. Then you work out if it's turbulent or laminar flow. Okay, so that's the general principle. So then we can have two types of flows. We can have external flow, so passing over a flat plate, for example, is external flow. Internal flow is when the fluid is passing through like a circular tube. For external flow, right, you use, let's use a Reynolds formula to work out if it's laminar and turbulent, or turbulent. If it's for an isothermal flow, for a laminar flow over an isothermal plate, the Nusselt formula you would use would be this. Okay. Again, these formulas will be given in the equation sheet. So this is for the local, and this is for the average. Okay, depending on what the question asks. Yeah. So okay, so you find out the Reynolds number. It tells you that it's laminar flow. Then you know, okay, do I need to use the local or the average, depending on how what the question says, and then you go and use the correct formula to work out the Nusselt number. If it's turbulent flow, this is the Nusselt number that you use, and if it's mixed flow, this is the number you use. Okay, let me go back. Again, like it could be entirely laminar, entirely turbulent laminar, or entirely turbulent. And here you have the Reynolds number. So remember, there's the critical Reynolds number. So it tells you the value above which turbulent flow will exist, and the critical length can tell you, so XC is the critical length. So if a Reynolds number is given and it asks you to work out the critical length, for example, a question can ask, at what point along the plate does this turbulent flow occur, right? So then if a Reynolds number is given, then you can work out XC. So XC is where the transition takes place. Went through this. So average heat transfer coefficient for laminar flow is this formula. This is the local for laminar flow over an isothermal plate. This one, actually, ignore that one. Yeah. And then you have this for the turbulent flow. Again, these formulas, you don't have to memorize them. They'll be given in the formula sheet. You just need to know how to use them and when to use them. So you can have mixed flow. That's when you have both laminar and turbulent. So then we can go into internal flow. So this is boundary layer development within a tube. So you have, this is the top of the tube, this is the bottom of the tube, and then you have flow. Notice how if it's just, so this is your normal velocity boundary layer, but because you've got a surface at the top, it also develops from the top down. So, and then they meet in the middle. So once they've met in the middle, then it's the fully developed region. Okay. Okay. So, and this is the same thing, but you have thermal effects. So you got the thermal boundary layer for this side of the tube, thermal boundary layer for the top side of the tube. As you go along, they meet. And then after the point where it's met, it's the fully developed region. Again, so for internal stuff, again, we do the same thing, work out the Reynolds number to work out if it's laminar or turbulent. And for circular tubes, this is a useful Reynolds formula to use, but this can be also very useful. But again, these will be given. And then these are the values. So you can have fully turbulent, turbulent laminar, and this is in the, so when it's the entry length, that's this part at the beginning. So the problem may ask you to deal with a point in the fully developed region, or it could ask you to deal with it in the entrance region. Okay, that's that. And then as an example, I just put over, this is a class question from one of the lectures. So this is water flowing. So water is the fluid flowing at a velocity of 1 meter per second over a flat plate. Yeah, so because this is a special case of a fluid flowing over a flat plate, we use this form of the formula to relate the average to the local. I won't go through it because I've done it stepwise already, but it's just simple integration to work out H bar here for two different temperatures. Yeah. If you have any questions, let me know. Okay, so I'll take like a 2-minute break, and then we'll move on to heat exchangers. In the meantime, if you have any questions, let me know. So my plan is to collate all the questions and answers from all of the lectures, and then put it all into one PowerPoint presentation, and then upload it to this week's Moodle page, so you can hopefully go through them and answer them yourselves and check my model answers against yours. Also practice on the past exam papers, but you will find that the past exam papers for my section are really easy. And so the questions, are these equations given in the equation sheet? Yep, they are given. Relevant equations are given. Are you able to share your note sheet as well? Yep, I will do. For last week's lecture, where did you get the question from? And is it possible to upload the notes too for that lecture? Last week's lecture, yeah, I will put. So I will put all the answers, the questions and the answers for last week's up. Yeah, I just haven't got around to it yet. I've done most of them, but haven't finished it yet. So I'll put it all up. Okay, let's carry on with heat exchangers. So, you should know the types of heat exchangers, and then heat exchanger questions using log mean temperature difference method. You should pay particular attention to parallel flow and counter flow systems. Yeah, so I haven't, in the revision notes, I haven't gone into the types of, the types of heat exchangers are, for example, concentric, tube and shell, compact, all these type of things, but they're in the notes, okay? So I didn't want to make these revision notes really, really large. So for concentric, right, which is a group name for the parallel and counterflow systems, you can have parallel flow, so you have the hot fluid, and then you have the cold fluid, and so for parallel flow, so let's say you have one tube, and then you have another tube. So one fluid in the inner tube, another fluid in the outer tube. Okay, is parallel because both fluids are traveling in the same direction. Okay, so the hot and cold mean fluid temperature distribution associated with a parallel flow exchanger is given here. So this is, again, you need to know this graph, understand this graph, see what's going on. So this is x is the distance. So x. So let's say the start is here and 2. So this is the start. And okay, so this and you got temperature here. So this graph is showing you the temperature change in the hot fluid. And so that's this one. So this is for the hot fluid. And this is for the cold fluid. So the temperature change as you go along the tube, okay, along the heat exchanger. So with increasing distance, the hot fluid loses temperature because it's doing heat transfer to the cold fluid, and this is the temperature drop profile. The cold fluid gains in temperature, and this is the gain temperature profile for the gain. Okay, so we must label everything appropriately. So THI, so temperature of the hot fluid at the inlet, temperature of the cold fluid at the inlet. At the end, you have temperature of the hot fluid at the outlet and the temperature of the cold fluid at the outlet. Okay, so this is the temperature difference at the beginning, right? And by the end, this is the temperature difference. So delta T1 is at the beginning because 1 is the start and 2 is the end, right? And you can see how heat exchange has taken place from the hot to the cold. Okay. These two lines will never meet, no matter how they get close. So this is important graph for you to know. Okay. What else? What else? Yeah, and this is the formula to work out or this, whatever, to work out the temperature difference, the log mean temperature difference. Again, formulas like this will be given to you, and you have to know how to use it to work. So often the questions are to work out the heat rate, right? As always, for conduction problems, convection problems, radiation problems, heat exchangers, whatever, Q. So it's the overall heat transfer coefficient U times the area times the delta T log mean, right? So we then, to work out Q, if U and A are given, we need to work out delta T Lm. So this is the formula to do that. We do a practice question later, and you will see it in action. Okay, so that was for parallel flow, and this is for counter flow. Okay, note how it's very different. So here, so let's say you have tube 1, tube 2. So you have the inner fluid going in this direction, the outer fluids going in the opposite direction. Yeah. So, so the temperature profile, so temperature against distance, x. So if this is 1, this is 2. Yeah. So the inlet of the hot fluid, so that's here. Let's say the center is the hot fluid. Obviously starts off hot, is in contact with the outlet of the cold fluid. Yeah. So this is the outlet of the cold fluid, temperature of the outlet of cold fluid, and that is here. So the temperature, so the hot fluid temperature profile is this. Yeah. So temperature of the hot fluid, TH outlet, TH inlet, and then TC outlet, TC inlet. And the temperature profile of the cold fluid is this. So the important thing here is the outlet temperature of the cold fluid, yeah, can now exceed the outlet temperature of the hot fluid. So this temperature, if the tube was long enough, yeah, this temperature can be higher than the outlet temperature of the cold fluid. Yeah. So note how it's higher than that. So basically, to summarize, know the difference, know how to draw them, label them, and understand what's going on with them. Again, you have the formulas to use if, when necessary, but they'll be given to you. So in special operating conditions where the heat capacity of the hot fluid is much, much larger than the heat capacity of the cold fluid, so that's here, right? Heat capacity of the hot fluid. So we're looking again at similar, like the temperature profiles, yeah? Distance 1 and 2, temperature. Because the heat capacity of the hot fluid is high, much higher, it's not going to change in temperature by absorbing or releasing heat to the cold fluid. Or, yeah, so the cold fluid absorbs heat from the hot fluid and increases in temperature, but the hot fluid does not change much in temperature because it has such a high heat capacity. So again, you should know, if given this situation, what the temperature and distance profile will look like. In the opposite case, when the heat capacity of the hot fluid is much, much smaller than the heat capacity of the cold fluid, you have the hot fluid temperature profile change, whereas the cold fluid stays stationary. In instances where they have similar or equal heat capacities, they both change. Yeah, so they both undergo the temperature profile changes for both. Overall energy balance formulas to use to work out Q when you're given mass flow rate. A dot above the M signifies its rate. Again, these will be given, just know how to use it. So this is a example question we did for a counterflow concentric heat exchanger, and we had to work out, so we had to work out how long the tube must be if the outlet temperature of the oil has to be 60. Okay, so we're given the inlet temperature of the hot fluid, we're given the outlet temperature of the hot fluid, we are given the inlet temperature of the cold fluid, we are not given the outlet temperature of the cold fluid, but we want to know, so the target temperature for the hot fluid, so the fluid we want to cool is 60 degrees. So how long does our heat exchanger have to be to do the job. Okay, so again, often we start with working out Q. So we can work out Q for the hot fluid using the hot fluid temperatures. Once we work that Q, we can then work out the temperature of the cold fluid, because remember Q remains the same, heat transfer. So we can work out Q, then plug it into a rearranged form of this formula, and we will get the temperature of the cold fluid. Then we know, so we want to work out L, right? So we know this formula where Q is equal to UA delta T. So we know A can be then expanded to this, so that we can make, so from that we can get L. So we first calculate the delta T using the formula. Again, these will be given if necessary. You don't need to remember. So plug in all of the values, because we know all of the values now, and we can work out delta T. So the overall heat transfer coefficient isn't given, but we know it's 1 over HI and 1 over HO. So this is where, in this, we need to work out if the flow is laminar or turbulent through the tubes. So remember, so we have one fluid flowing here, so the water flowing in this part of the tube and the oil flowing in this part. So we need to know both if the water is turbulent or laminar flow, and if the oil is turbulent or laminar flow, to work out the heat transfer coefficients, or determine the heat transfer coefficient. So because this is flow through a tube, so it's internal flow, right? This form of the Reynolds number calculation is useful. Okay, again, if necessary, it'll be in the formula sheet. You don't need to remember this kind of stuff. Yeah, so plug it in slow. So with a value like this, which is quite high, we know the flow is turbulent. So we know we use this form of the Nusselt formula, and we work out a Nusselt number of 90. We know also that H is equal to the Nusselt number times K over D. K is given in the question, and so we can work out HI. So to work out L, we need to work out delta T, and we need to work out U. To work U out, we need H values. To work out H, we need to know if it's laminar or turbulent flow. To do that, we find the Reynolds number. Once we find the Reynolds number, we know, okay, it's turbulent flow. Then we use the correct form of the Nusselt formula to work out ND, and then we use this formula to work out HI. Okay, so that was for the oil. Okay, so we've got two types of flow. Then that was for the water, sorry. So this is for the water. And now for the oil, we work out the HD, which is we work out this diameter, essentially, which is the outer diameter minus the inner diameter, because the oil is flowing through this part of the heat exchanger. So again, we use this form of the Reynolds number, and we get a Reynolds number, a very small Reynolds number. So then we know it's laminar. Then we can plug it into to work out NU, and then rearrange to make H the subject, and then we got HO. So then we can now go back and work out U, and then now we got delta T, we got U, and then we can expand that to get L. So rearrange, and then we get the length. Okay. So we need a length of 65.9 meters to achieve an outlet temperature of the oil of 60 degrees. Okay, let me just check if there are any questions. Any questions? Is that clear? So overview type is like we looked into detail in terms of conduction, convection, in isolation, right? Like the theory behind it and their application individually. Then we go into systems like heat exchangers, right? Where we apply those to work out Q for heat exchangers or the length. Okay. Okay, so I'll give like a 2-minute break and then we'll go into vapor and combined power cycles. Okay, there are no questions, so I'll carry on. The next topic is vapor and combined power cycles. So here you should be familiar with temperature entropy diagrams, right? This is important, important to understand. So this is the saturation line, right? So the middle region is a region where you have both liquid and vapor and gas, or let's say vapor. Here you have only vapor, and here you have liquid. Above this line, this is the supercritical line, you have you have the supercritical fluid, right? This is when the liquid particles are vaporizing extremely rapidly, that the density of the liquid and the vapor are equal. So you should know how to understand this and use them. So if you have a point on a line, right? So if a point of interest is here, it means it's a saturated liquid. If a point of interest is here, for example, on the line, then it's a superheated vapor, right? And if it's further along, it's more superheated, I guess. So if it's somewhere along here, it's going to be a mixture of liquid and vapor, and that the quality or the content of the water, the liquid, is given by the X value here. Okay, the formula is there. Okay, so this is important because then you kind of have to go to the correct vapor, the steam table, and then find the values that you need to find. So for my section, in this year's exam at least, if questions, I don't ask you to go and look at steam tables. So this is just for my section. I don't know about Dr. Lewis. I just give you the values from the necessary values from steam tables if necessary. Okay, so because he does a lot of the steam table stuff, I didn't want to add that to you. So then we looked at vapor power cycles. So this is all for the application of vapor power cycles. Okay, so the simple one is the Carnot cycle. So it's a simple steady state flow cyclic process. So this is the Carnot cycle. Yep, cycling through your TS diagram. So you have from point 1 to 2 the fluid here. So because it's here, it's a saturated liquid, right? Is reversibly and isothermally at constant temperature because it's going. This is temperature, right? Is heated in a boiler. So this takes place in a boiler, right? To a superheated vapor is formed, right? Then the fluid, so it's going from a liquid to a vapor. Then, liquid to a fluid. The fluid is then expanded. So as it expands, it does work. So this happens in a turbine. And that work, so it turns the turbine, and that is used to generate electricity or whatever. So this is the whole point of this cycle, is to generate power for us, okay? Once it's generated that power, it's turned the turbine, you go from a condensed, so it's a condensed, so what you get here is a mixture of fluid, a mixture of vapor and water, right? Because it's in this region of the TS curve, and then it's condensed to form a liquid, more of a liquid, so increase the water content in a condenser so that we can start the cycle again. So then it's compressed isentropically in a pump, so pump, to go back to point 1, and then it repeats. So you go round and round and round, and you generate power. So the thermal efficiency for the Carnot cycle is 1 minus the temperature, the low temperature reservoir divided by the high temperature reservoir. Okay. There are a couple of issues with the Carnot cycle. So steps 2 to 3. So this is 2 to 3, right? So after it goes through the turbine, it lands in point 3, right? Which contains a mixture of liquid and vapor. So this is highly impractical and can cause erosion problems for the turbine. So it can be expensive. So that's not ideal. The second thing is we have to, so this is then condensed here, right? And then a pump point. So then a pump is involved, which then has to deal with both the vapor and the liquid, and that is very difficult to design a pump that can handle both. Okay, so so that's not ideal. So these two steps are not ideal, and then therefore the Carnot cycle is not a good model for this. So then we come into a better model, which is the Rankine cycle. So two major differences is that step 2 to 3 is carried out beyond vaporization to a superheated vapor. So remember last time it stopped there, but for the Rankine cycle, we continue further and superheat it, right? The reason we do that is then in the turbine step, after the fluid has gone through the turbine, it then lands very, very close to the saturated line so that the water content is very low, which means that there's less damage caused to the blades of the turbine. So step 4 to 1, right? The cooling steps brings about complete condensation, giving a saturated liquid. So last time for the Carnot cycle, we stopped here, right? Where there's going to be both liquid and vapor. But now we take it all the way to the saturation line to just the liquid, saturated liquid point, which means that the pump can deal with it. It doesn't have to deal with a vapor and a gas, vapor and a liquid. So steps 2 to 3 and 4 to 1, which were the problem here, are taken care of. If we look at the steps a bit closer, so let's look at step 1. So it's a reversible isentropic pumping of a saturated liquid to the pressure of the boiler. Okay, so it's pumped to the boiler pressure. So this is a compressed subcooled liquid is formed, right? So that's step 2. So note that some work is input. So we have to supply energy, which is costly, right? To do this work from point 1 to point 2. However, right, the work that we get out from the turbines changing, so this is our main goal, right? We want to maximize the work out, is much larger. So even though we put in some energy, put in some work, what we get out is many times more. So it's still worth doing. Step 2 in detail is you have the subcooled liquid and you heat it all the way to step 3, right? Vaporize it. This all takes place. This part is at constant temperature, and then you go further up here. Okay. The reason we go up here is so that we can bring the end point of 4 as far towards the saturation line as possible, so that we're dealing with high quality steam. Okay. Then we have the most useful step for us. We have the superheated fluid condensing down, turning the turbine and coming to point 4. So again, this is a reversible isentropic expansion. It's close to the saturation curve because we heated it to point 3, superheated it at point 3. Then at constant temperature, we condense the vapor to a saturated liquid, and then we go again. Okay, that's essentially it. energy analysis, so important formulas for you to be able to use, but you don't have to remember them, are these. And then the thermal efficiency is given by 1 minus heat out, so the heat given out divided by the heat put in. And yeah, that is that. Okay, so that's the revision lecture. I have example questions with model answers for the vapor fluid stuff is on Moodle already. Essentially, it's looking at steam tables. So I didn't want to go through it. It would just be me going through and looking at steam tables, but you don't need to do that. Those values will be given to you if necessary. Any questions?
How long is the exam?
The exam is, let me check, it's 2 hours. 1 second, let me double check that for you. Let me open up. Yeah, 2 hours. 2 hours if you don't have any DSS needs. Hold on. Let me read that question. When you say it's going to be different, how will it be different? How will the questions be different? So different in sense, in the previous years, the exam questions don't go into, they're really quite straightforward. They don't go into much depth. They just like work out Q, and you have all the necessary information given to you to work out Q. So you just have to plug it into the formula that's given in the equation sheet to work out Q. So this time round, you would have to first work out other components to work out the final Q value. You know, it's more stepwise. There's more depth to it. That's what I mean. Will the Carnot cycle diagrams be included? What do you mean included? So if a question on that stuff comes up, that those TS diagrams will be given to you, right? You don't have to draw it or anything like that. You just need to know how to use it. You need to know if the point is on a saturation line, then what that means. If it's not on a saturation line, what that means. That's the kind of thing. But the diagrams will be given to you. But yeah, my top tip is practice with questions and practice, as much of the questions we went through in the tutorials, in the lectures, and in the revision lectures that we did last week. I will put up all of the answers for the revision questions on Moodle. Maybe today, if I can. I've done up to question 5. I'll put, and I think there were like 6 or 7 questions. So, yeah. Yep. I could put the answers for all of them last week. Yeah. So yeah, for you'll notice if you look at the past exam paper questions, and then you look at how simple they are compared to the practice questions that we do in the lectures and tutorials, right? So there's a bit of a difference. So the exam questions you're gonna get are gonna be similar to the kind of closer to the complexity of the practice questions in the lectures and tutorials than they are to the past exam papers, if that makes sense. Yeah. that's it. But I think they're all very, very doable, right? So it's not. I personally don't think it's difficult. I would say it's closer to the practice questions than the exam questions. If any, has anyone tried the practice question, exam questions, past exam questions? Anyone? Aliza, maybe you or?
Not yet.
Okay, yeah, you will see if you do it. They are very simple, too simple for too many years. So that's why it's just made it a bit more complex. Again, if you have if you try practice questions and there's parts you don't understand, or even if you try past exam questions, there's parts you don't understand, and you want me to explain it or have a look for you, then you can message me on Teams or send me an email with I don't know, yeah, with the questions you have or where you're finding it difficult, and I can try and explain, or I can explain. No, exam questions are on past exam questions are you have to get it yourself via the app or something. They're not uploaded. I don't think all of them are uploaded to Moodle. If you want, yeah, yeah, and then the practice questions are the ones that we went through in the lectures and tutorials. Those are on Moodle already, apart from last week's one, where the questions are, but the answers aren't. All good? Any other questions? Of course, I mean, yeah, they're going to be printed soon because your exam's coming up in less than a month. Yeah. The yeah. Anything else? I would say tips wise, yeah, practice questions. Or yeah, practice questions and yeah, get comfortable using the equations and yeah, that's what I would say. You must practice, practice, practice. And then if you can time yourself as well when you're doing practice questions, um, so that would be good. Just to understand how long it's taking you, because you obviously, let's say it's a 2-hour exam, you have 1 hour to do my questions and 1 hour to do Dr. Lewis's. So you should time yourself. Yeah, Eliza, did you have a question?
How many questions are in the full paper
6 questions.
for both sections?
No. Six questions in total. So 3 questions from Dr. Lewis, and you have to answer 2 of them. 3 questions from me, and you have to answer 2 of them.
Okay.
Yeah? Yeah. Yeah, it will be 3 questions from my part and 3 questions from Dr. Lewis's part. Do you have any other exams in May? Or is it just for thermodynamics?
We have 2 other exams.
Okay. Okay, fine. Yeah. Any other questions? Yeah, the recording will be available via the Teams, like in the Teams link. It'll be there for you to listen to. Cool. Okay. So if you have no other questions, then we can end it here. And if you have any questions that come up later on, feel free to email me, or on Teams. In the Easter break, if I look at my Teams or my email, then I do answer, I do reply, I don't ignore it. But sometimes I if I'm not on my laptop or my phone, I don't check. So you're welcome to email me and I'll try my best to get back to you. Okay, let's end it there then. Thank you, everyone.
Thank you.
Thank you.